I thought I was recording, but I'll check it again. Thanks for reminding me. I clicked on it, but I'm not sure if it went. So concentration has many different units. You'll see a bunch of them out there. So one of them is grams per cc. Another one would be milligrams per deciliter. Another one would be percentage. Another one, the one we're going to focus on here, is moles per liter. And the moles per liter is called molarity. Okay. And in a sense, you can think of it sort of like a density. Density is the amount of something divided by its volume. Molarity is the amount of something divided by the volume. It's just that the units are not in grams or milligrams anymore. They're in moles. So specifically, molarity is equal to the number of moles of the solute divided by the number of liters, that's a volume unit, of solution. Think of a 1 liter bottle, right? So remember, the solution is the mixture. So the volume is how much space it's taking up, right? So the number of liters of solution, that's how much space it's taking up. And then you're taking in the numerator, you're putting how many moles of these little solute particles are there. So the more solute you put in there, the greater the number of moles. And so if the number of moles increases, it's true the volume might increase a little bit, but generally, interestingly enough, when you dissolve things into water, the volume doesn't change very much. It just distributes the solutes into the water. There we go. So as you increase the number of moles, the liter stays about the same, so the molarity increases. Okay. Now there's a symbol used for molarity. So you might see this number, 1.0 capital M. If it's a capital M, that's the abbreviation for molarity. Okay, so it is important that it be a capital M. A lowercase m actually has a different meaning. So if you see a number with a capital M, that means molarity. So that's the number of moles in the solution. So let's take a look at a few calculations. So let's calculate the molarity of a solution with 0.052 moles of sodium chloride dissolved into 250 milliliters of solution. So when you see these problems, you'll often see the wording in a particular way. It won't say 250 milliliters of water. It'll say 250 milliliters of solution. And the reason for that is that if you measure out 250 milliliters of water, and then you put the salt in it, the volume will change somewhat. So it's important to have it known what the solution volume is as opposed to the volume of the water. If you only know the volume of the water, not the solution, it gets to be kind of a complicated calculation. So typically they'll tell you the volume of the solution, the total mixture right here, okay? So it's a relatively simple calculation. There is one issue here, which is the units are in milliliters. They're not in liters. We need to have them be in liters, right? So molarity, I'm going to use capital M for molarity, is the number of moles. So that would be 0.052. And then we need to divide that by the volume, but the volume is in milliliters. So here's how we can deal with that. 250 ml, and it's 1 liter per 1,000 milliliters. It's 1,000 to 1, not 100 to 1, but 1,000 to 1. And so that'll give you 0.250 liters, right? Milliliters cancel.
Yes, dear.
Go ahead.
Times.
Oh, interesting. Okay. So what is that? 0.104, 0.208, right? And you have a couple of options for reporting the units. You could just do it with moles over liters. That's perfectly fine. Or you could use the abbreviation capital M. And most chemists will use they'll use the abbreviation, the capital M. But for calculations, it's not a bad idea to put MOL divided by L, because that way you can sort of see what the units are and you might need to use them in a future calculation. Okay. So keep in mind, it's the number of moles of the solute. So if you're dissolving sodium chloride into water or sugar into water, it's the stuff you're dissolving in, the sodium chloride or the sugar. That's the solute. So it's the number of moles of that divided by the number of liters of the solution. And here's your conversion factor between milliliters and liters. Okay. Any questions about that one? That's sort of the simplest one. Okay. The next step is what typically when we measure things, we typically weigh things. We weigh the solute. Okay, so suppose that we weigh out some sample of the solute. So let's use a different solute. Let's use table sugar. Let's use sucrose, for example. Sucrose has a formula C12H22O11. Okay, and so let's say we weigh out 35 grams of sucrose. And added to, let's make it 150 milliliters of solution. Okay. Now, actually, it's interesting to pick the 35 grams. It's around 40 grams of sucrose, high fructose corn syrup. So that's essentially sucrose. It's around 40 grams in a bottle of Coke or in a can of Coke or Pepsi or any of those drinks. So this is about the amount of sugar that gets added to one of those soft drinks. So it's 35 grams. That's how much is weighed. And it's going to get added to 150 milliliters of solution. And we just want to calculate the molarity of the solution.
Can I ask a question?
Mm-hmm.
Why is there a decimal point after a whole number in these problems?
I'm doing that. I never used to do that, but I've been doing it because
I mean, Alex says you have to do that.
yeah, I've been reading these Alex problems, and they always keep putting a decimal point after. To be honest with you, I've never seen the requirement to put a decimal point after a number that doesn't have 0 in it. Like typically, the reason you'd want to put a decimal point, let's say you have 30, is to tell people that this number here is significant, because 0 is dealt with a little differently than 1 through 9. So, I don't know why they decided to do that, but
Okay.
I'm just going to stay consistent with it.
Okay, thank
It's not
you.
a bad idea. It doesn't hurt. So
Just
why not?
curious.
Right. Yeah. I mean, to be honest with you, in that context, I think it's kind of like this, I don't know if you've noticed, like people in math and science will write numbers, sometimes they'll put a 0 in front of the decimal point and sometimes they won't. There's no requirement that you put a 0 in front of the decimal point. It's just sort of
A tradition.
yeah, I think so. I think that's really what it is. Okay. So 35 grams of the sucrose is weighed and added to 150 milliliters. So remember, we need to know the number of moles. If we're going to calculate the molarity, we need the moles of the solute. And the solute, again, would be the sugar. And then we need to divide that by the number of liters of the solution. So we don't have the number of moles of sucrose. It's not given. It's actually given as a mass. So what we have to do is we have to convert that to moles. So we'll take the mass of sucrose and we'll convert that to the number of moles of sucrose. And then, of course, the way we do that is by using the molar mass. This is the calculation we learned to do back in chapter 3. So let's find out what the molar mass of sucrose is. Okay, so we got C12H22O11. Well, that's 12 carbons, 22 hydrogens, and 11 oxygens. So it looks like it's 342 point, let's see, was that 2234 grams per mole. So there's the molar mass of sucrose. Okay, so now we do our conversion. 35 grams of the sucrose. And then 1 mole weighs this amount. So 1 mole of sucrose is 342.34 grams. Okay. All right. So let's 35 over 342. Let's find a little calculator here. Got to have mine in here. There it is. So 35 over 342.34 is 0.1022. And then now we again, we have our volume is 150 milliliters, so 150 ml. And it's 1 liter per 1,000 ml. So that gives you 0.150 liters. So now our molarity is easy to calculate. 0.1022 over 0.150. Okay, so 0.1022 divided by 0.150. Looks like it's about 0.682. And again, you have 2 ways in which you can report the units. You can either write it explicitly as moles per liter, or you can just write it with a capital M. So right there, that tells you that, you know, that's around 0.7. It's close to 0.7. That's the molarity of sugar in a can of Coke, right? It's around 0.7 moles per liter. Okay. Pretty high concentration, very sweet. Okay, any questions about that calculation? Good, okay. So moles divided by liters. So just remind yourself moles over there. You gotta have moles, you gotta divide that by liters and you're set. Now, I will point out a couple of sort of eccentricities about the units when you see all these kinds of problems. So for example, let's say you were told you've got 2.5 millimoles of sodium chloride. So there's your salt. And then you were told you've got, I don't know, 100 milliliters of solution. So, and then we want to calculate the molarity. Well, what you could do with this one is you could say, wait a minute, that's millimoles. It's not moles. So I might convert that to moles by using a milli conversion. And that's not in liters, it's in milliliters and do the same conversion. But if you take a look at it, if you take 2.5 millimoles and you divide that by 100 milliliters, the milli will actually cancel out, and that'll leave you with the correct units. So be kind of careful. Don't be too mechanical about this. Take a look at what the units are and see if they can work out for you. There would be nothing wrong with converting this to moles per liter. So for example, I could say 1 liter is 1,000 milliliters. And that would give me 0.0025 moles. And I could do the same thing here. Oops, sorry. 1 mole is 1,000 moles, millimoles. Let me write that a little cleaner. One mole is 1,000 millimoles. And then I could do 1 liter is 1,000 milliliters. And that would give me 0.100 liters. And then you could take, 0.0025 moles, divide that by 0.100 liters, and that would give you the same answer. But there are cases, you'll see individual problems where you actually don't need to do all those conversions. If you can just recognize, oh yeah, that's milli and that's milli, they'll cancel out, then that can save you quite a bit of time. Okay. Another issue that comes up is that sometimes we want to know not the concentration of the solute, but the concentration of part of the solute. For example, suppose that we take barium chloride dissolved in water. Okay. Here's what happens when barium chloride dissolves. Remember, barium is in the second column, so that means it has a charge of +2. So when you dissolve it into water, there's our symbols for dissolving things in waters, it breaks up into separate ions. So you get a barium ion, but notice there's a 2 there. So you get 2 chloride ions. Right? So that has an effect in terms of what's actually in the water. Every time you dissolve 1 mole of barium chloride, you get 2 moles of chloride and 1 mole of barium. So suppose I said the following: dissolve 0.250 moles of barium chloride into 250 milliliters of solution. Calculate the molarity of the chloride ion in the solution. Okay. So that fact that it forms 2 chlorides has an effect, because what happens is if we have 0.250 moles of barium chloride, the equation tells us that we've got 2 moles of chloride for every 1 mole of barium chloride. So I'm going to multiply that by 2 to 1. So actually the amount of chloride is twice as much. Okay, it's not 0.25, it's actually 0.5. So be careful with that. If you have an ionic compound and the question is what's the concentration of one of the ions in that solution, then just make sure that you see what the relationship between that ion and the compound is. So now when we calculate the molarity, we would use the 0.500 moles and then divide that by our 0.25 liters. And so you get 2 moles per liter. Okay. Now, if the question had been about the barium would be half of that, right? Because the barium, you only get one barium for every one barium chloride. So in that case, this 2-to-1 ratio would just be 1-to-1, and you'd get 1 mole per liter for the barium. Okay. So read the question carefully. If it's asking you about one of the ions, make sure you know what that concentration of the ion would be relative to the compound itself. Okay.
I have a question.
Go right ahead.
So in working in Alex to do the homework, it seems to put the problems in a random order. Is that accurate? Like the first problems in the Alex homework were these problems. Do you know if there's a way to do it where you're doing it in the order of the chapter?
That's the first I've heard anybody say that. Anybody else having that issue?
No, my questions were actually in order.
In the order of the chapter?
Mine weren't in
Mine
order.
is not in the order. It's random.
Because I kind of expected to be able to go through the problems in Alex in the order of the chapter so that I'm learning them in that order, which is...
No, that's what I would want it to do.
Yeah.
I'll check into that.
Okay, thank you. I didn't know if I was just
The only thing
doing it
the only thing that I could think is that it has to do with your initial knowledge check.
I definitely didn't know any of this chapter in my
Okay.
knowledge.
Yeah. So if that's the case, so we have to take a look at it. That's an interesting issue. So at least a couple of people, that's happening. Okay. All right. So that's molarity, right? And the next issue that comes up is the issue of dilutions. So dilution is kind of an interesting calculation. It's actually a relatively simple calculation, but the background's a little complicated. So here's the idea. Imagine that you've got a cup full of a solution, right? A mixture, homogeneous mixture. So I guess, just to keep things relatively simple, we'll make it sugar. But this time I'll use glucose instead of sucrose. So I'm just drawing you a little picture here just so you can imagine it, right? This is a picture of a solution. You've got the water. By the way, when you talk about water, the reason that water has this shape, this is called a meniscus, which your eye also has a meniscus. It has this sort of concave bending to it. The reason for that is that water is very highly attracted to itself. The hydrogen bonds in water essentially cause the molecules to really contract onto each other, and they pull in very, very tightly. And so the water molecules are pulling in toward themselves. But in glass, if you're using glass, water molecules are also attracted to glass. So they will also be attracted to the glass and actually climb up the walls of the glass a little bit. The water molecules will climb up because they're so strongly attracted to it. So those are called adhesive and cohesive forces, okay? The cohesive forces are the attractions between the water molecules, and then the adhesive is the attractions of the water for the glass. So if you were to use some kind of plastic that isn't attracted to water, then what would happen is that water would be flat on the surface. It wouldn't have this bending that you see right there. And so, if you think about other liquids, for example, mercury is a liquid. Mercury is an amazing substance because it's the only metal that's a liquid at room temperature. Most metals are solids at room temperature. None of them are gases at room temperature, but mercury, it has a melting point that is low enough that it actually liquefies at room temperature. And mercury is not attracted to glass at all. So what happens is if you were to fill up a cup with mercury, you would find that the mercury would actually take on a different shape. It would actually bend upward away from the glass like that. So this is water mixture because we've got solute in there. And then this is mercury. Mercury is used in thermometers even to this day, and barometers, which are pressure meters, because it's a liquid and you can measure temperature and pressure in a capillary with liquids very easily. So mercury is highly dense material, so it's good for those sorts of things. Okay, and you can actually make solutions with mercury. You can dissolve other things into mercury, just like you can dissolve things into water. But what you dissolve into mercury is very interesting. You can dissolve other metals into mercury. So if you take a piece of iron or a piece of sodium, you can actually get the atoms. They don't form ions, they just form atoms. They actually will dissolve in the mercury. So these are metal atoms. Metal solutes. Okay. And so actually dentists have done that over the years. So a dentist will use mercury and another metal, dissolve the other metal in the mercury, and then you get a solution which will solidify over time. It's called an amalgam. And I don't know to what extent they use them anymore because mercury has certain issues, toxicological issues, but it's an amazing property of it. Okay. So let's talk about the dilution issue. Let's imagine that we say, hey, you know, this has got sugar in it. It's got glucose. It's a glucose solution. And let's say that the concentration of the glucose in the solution, in the mixture, is, I'm going to make up a number. Let's make it 2.5 moles per liter. So capital M for moles per liter. Okay, so there's our concentration. And what we're saying is, suppose that concentration is just too high. So I'm trying to drink this solution. It's just way too sweet for me to enjoy. So what I'm going to do is I'm going to dilute it. I'm going to make it less concentrated. And that's what we do in a dilution. So dilution is you take a solution at high concentration and you add water to make a solution at lower concentration. So here's how we might do that. We might take that original cup of glucose solution, and we're going to give this a name. We're going to call it the stock solution. The stock solution is the solution that has a higher concentration. And then what we're going to do is we're going to take some of it out, right? We're just going to take some of this stock solution. So I'm just going to sample it, take some of it out, and put that amount into another container. And then I'm going to add water. Okay, so what happens? Essentially what you end up with is you get some of that glucose solution, but now it's less concentrated, right? It's not as concentrated as it was here because we added water to dilute it. So now we have a less concentrated solution. And this is called the dilute solution. Okay, so higher concentration solution is called the stock. Lower concentration solution is called the dilute or diluted, either one, dilute or diluted. And there is a very nice little simple relationship that relates the concentration of the stock to the concentration of the dilute. It's very
Just
simple.
FYI, Alex calls that the working solution,
Which one do they call the working?
the dilute solution.
Okay, they call it the working. Yeah. Typically people call it the dilute. So the relationship is the molarity of the stock solution times the volume that you take out. Okay, so V of the stock, right? So that's not the volume, it's not the entire volume of the stock, it's just the amount that you take out. Okay, is equal to the molarity of the dilute solution times the volume of the dilute solution. This is sometimes referred to as the dilution equation. Okay. And your textbook uses some different notation than this one. I will show you a couple of different notations. Sometimes it's written as M1V1 equals M2V2. This is probably the most common way that it's represented, M1V1 equals M2V2. Another way would be C1V1 equals C2V2, where C refers to concentration instead of molarity. You're just saying concentration, but really you mean molarity. And so this solution can, or this equation can be used for most dilution calculations. Okay, you just have to be careful what it means. What it's saying is you have a concentration here. So I'm going to call that MS, molarity of the stock solution. And then you're going to take some of it out. The amount that you take out is the volume of the stock. So we're not talking about the total volume of the stock, just the amount you take out. And then over here, once you add the water, now you'll have a molarity in this dilute solution, and this total volume is the volume of the dilute. And keep in mind, the volume of the dilute has got to be greater than the volume of the stock, right? Because you're taking some of the stock, let's say you're taking out 25 milliliters, but you're adding water, right? So if you're adding water, your volume is going to be more than 25 for sure, right? So that means that the volume of the dilute will be greater than the volume of the stock, okay? And mathematically, if this number here is bigger than this number here, that means this one over here has got to be smaller than that one. That's the only way it works out mathematically. So that also means the molarity of the stock will be greater than the molarity of the dilute. Okay, so you start with a higher concentration, you finish with a lower concentration. You start with a smaller volume, but you end with a larger volume. So let's take a look at a calculation. And I'm going to write this up here again. Times Vs equals Md times Vd. Okay. So here's an example. We wish to make a hydrochloric acid solution with a concentration of 0.050 moles per liter, molarity. Oops, let me take that little period out. And a volume of 250 ml. If we start with a stock solution of let's make it 1.75 molar. How many milliliters of stock solution do we need? Okay, so typically when you do dilution problems, they're relatively lengthily worded word problems. Not always. You could make problems that are simple calculations, but usually they're long word problems. So what I would recommend is you read it over a couple of times and then just start identifying what they're referring to. So we want to make a hydrochloric acid solution with a concentration of 0.05 molar. Well, if you want to make that solution and you want to have that concentration and that volume, that's where we would, yeah, I mean, that's not a bad idea to call it the working solution, right? That's the solution you want to work with. So that would be the dilute solution. Typically, we want to make the dilute solution from the stock solution because you can't make a stock solution from a dilute solution. You can't go backwards, okay? So that would mean that the dilute solution, we have a couple of numbers here. It's 0.05 moles per liter, and the volume is 250 ml. Okay. What's interesting about this problem also is it doesn't matter that it's hydrochloric acid. It could be sulfuric acid, hydrochloric acid. It's, the calculation is the same. Doesn't matter what the substance is. Okay. And then we're going to start with the stock solution that has 1.75 molar. So that means our stock, it has a molarity of 1.75 moles per liter. So then the question is, how many milliliters, right? So that means they're really asking us for the volume of the dilute solution. That's really what they're asking for. They do want to have it in milliliters, okay? So let me draw a little picture for you just so you can see what's happening.
They're asking for the volume of the stock.
Yes, I meant to ask. Thank you.
No problem.
So here's your stock, and it's 1.75. Okay, and we're really asking how much of that do you have to take out and to make our dilute solution? Okay. Knowing that this is 250 ml and knowing that this is 0.050 moles per liter. Okay, so you're really just trying to figure out how much is going over there. So let's use the equation. MS times VS equals MD times VD. We're asked for the milliliters of stock solution. So that means we're trying to figure this one out here. So what you do is you divide both sides by the molarity of the stock. The reason you divide it is that if you divide this side, the left side, by that, you get 1. And so that leaves you with the volume of the stock is molarity of the dilute times volume of the dilute divided by molarity of the stock. Now let's go ahead and put everything in with the units. I recommend putting units in just to check because you don't want to be off. Often when people do these problems, they're off by 1,000. And you don't want to make that happen. You don't want that to happen. So the molarity of the dilute is 0.05 moles per liter. I'm going to put the units in just so that we can see them. The volume of the dilute is 250 ml. And then the molarity of the stock was 1.75. So let's go through our dimensional analysis. Moles divided by moles is 1, right? One's in the numerator, one's in the denominator, so they cancel. 1 over liters divided by 1 over liters cancels. So that means that when you do this calculation, the volume of the stock is going to be in milliliters. Okay. Now it's just a matter of doing it. What is it? 0.05 times 250. So 0.05 times 250 divided by 1.75. Looks like it's around 7.14, 7.1. ml. Okay. So what that means is, if you think about the numbers here, right? What you're doing is you're taking this stock solution, you're taking out about 7 milliliters. And 7 milliliters is not very much. If you actually look at like a cup, 7 milliliters would be the bottom of this glass, but only going up about maybe about a centimeter. So it's really just a small amount. This right here is probably about 150 milliliters to here. Okay, so 7 would just be about that. So 250 ml, which would maybe be to about right here. You're making that a much. You're taking the concentrated solution, the stock solution is only that amount, and then you're diluting it up to about right here with water. Okay. And so that will give you a concentration that started off very high, 1.75 is a pretty high concentration. So it started off at 1.75. It went all the way down to 0.05 because we just took a little bit of the stock solution and added a lot of water. Okay. Any questions on that one? Okay. I'm going to show you one more. And with this one, I want to go over one that has different prefixes because sometimes you'll see different prefixes. So let's take a look. I'll save this one. And then let's look at one more. Okay. So again, another dilution. Okay, so for this one, we're going to dilute 10.9 milliliters of 46.1 micromolar until the concentration falls to 30.0 micromolar. Okay. Calculate the volume of water that must be added to the stock solution. Okay. So this one's a little different. It's got one little additional step here that I want to point out for you. Okay. So what are we doing? We're taking 10.9 milliliters of a particular solution. So actually I should put in here stock solution. Okay. Sorry, that goes right in there. So dilute 10.9 milliliters of 46.1 micromolar stock solution until the concentration falls to 30.0 micromolar. Calculate the volume of the water that must be added to the stock solution. So here's what we're doing. We're saying the following now. It's a little different than the previous one. You got your stock solution. And the stock solution is 46.1 micromolar. Okay, don't be scared by micro. Micro just means 10 to the minus 6. And what we're going to do is we're going to take 10.9 milliliters of it. So I'm just going to draw a little picture here. This is the amount we're taking out of it. We're going to take out 10.9 milliliters of the stock solution. And then we're going to dilute it into a container. And now we want the concentration to be 30 micromolar. Okay. So there's 10.9. We know there's 10.9 in here, right? Because we know we put 10.9 milliliters into it. That's how much we put in. But now what we're asked for is how much water did we add? Right? And so this one we have to deal with a little bit differently. And the reason is the dilution equation doesn't tell you how much water to add. It just tells you what the total volume is of the dilute solution. So we'll use it. We're going to say molarity of the stock times volume of the stock. Remember, the volume of the stock is the amount that we move into the dilute solution, is equal to the molarity of the dilute. I'm sorry, yeah, times the volume of the dilute. So here's the first step. We're going to calculate the volume of the dilute solution. Okay, because that's what you can do with that equation. We know the molarity of the stock is 46.1. We know the molarity of the dilute is 30.0. And we know the volume of the stock that we're transporting is 10.9 ml. So we know those three. So that means we can calculate the volume of the dilute. So volume of the dilute would be volume of the stock, molarity of the stock times volume of the stock divided by molarity of the dilute. So molarity of the stock is 46.1 micromolar. Volume that we're transporting over is 10.9 ml. Divide that by the concentration of the dilute, which is 30.0 micromolar. Take a look at the units. Micromolar, micromolar, they cancel. So no need to convert this to moles per liter. Just leave it in micromolar. So now you have 46.1 times, oops, I've already forgotten what that number is, 10.9 over 30. And it looks like you get about 16.75. And then the units are right here, milliliters. Okay. Now, what is that volume? That's the total volume. When you do the dilution equation, M1V1 equals M2V2, that's the volume of the dilute solution. So that is 16.75, right? But the question was, calculate the volume of water that must be added. So it's not asking us for that 16.75, it's asking you for how much water was added. Well, we know we started with 10.9, and now we know the total is 16.75. So the volume of the water that gets added would just be your 16.75 minus the 10.9. And so what is that? 6.75, 5.85. And there you go. Okay. So be careful when you read these questions on ALEKS. Sometimes it may ask you for what volume the dilute solution is. Other times it might ask you what volume of water is getting added. In case it's asking for that, then you'll have to do this second step here. Okay. There you go. So that's dilution. There is a type of dilution problem called serial dilution, where you take one stock, you dilute it to a dilute solution, and then you dilute it again, and then you dilute it again. That's called serial dilution. The calculations are pretty simple, but you don't need to worry about that type of problem in this class. Okay. That's something you would deal with in an analytical chemistry class. And there you go. Okay. And that's pretty much, excuse me, that's pretty much all the topics from chapter 4. Dilution is the last one. Concentration of solutions is what it's called. And really there's 3 types of problems. The first one is you got the number of moles of the solute, you divide that by the volume of the solution, that gives you molarity. The second one is they give you the mass and you use the molar mass to figure out the molarity of the solution. And then the third one is the dilution calculation, and that'll pretty much get you through that topic. Okay. Any questions?
I have a question.
Sure.
Could you, and I don't know if anyone else needs this besides me, but could you either do like a brief algebra review on how to change that formula to work for different solving fors, or just give us the formulas for solving of each of the 4 components of the formula?
So one thing you want to be able to do is you want to be able to do this kind of algebra because it's going to be really important in chapter 10. You have to do it a lot in chapter, and actually chapter 5. 5 and 10, it's a lot of this type of problem. So here's the idea. And we'll use the dilution formula as an example. One of the things that's nice about these types of problems is there's no addition or subtraction. It's all multiplication and division. And so the algebraic approach to multiplication and division is you do the opposite. So if you have something times something, you divide it. Right? So you do the opposite. And so the idea here is the following. If I take 3 divided by 3, that's equal to 1, right? If I take 6 times 2 over 6 times 2, 6 divided by 6 is 1, right? 2 divided by 2 is 1. 1 times 1 is 1. So that's also equal to 1. We can expand this not just to numbers, but to actually symbols, because the symbols are representing numbers. So if I have M1 and I divide that by M1, there's only one example where this is not true, and that's if M1 is 0. 0 divided by 0 does not give you 1. But if it's any number other than 0, this would be equal to 1. So here's what happens. If I take M1 V1 and I say that's equal to M2 V2, and let's say I want to find M1. What you do is you look at the side of the equation that has M1 in it. Okay, well, here it is right there, right? Notice it's not M1, it's M1 times V1. So we just want M1. So what you have to do is you have to eliminate V1 to get the M1. If it's multiplication, you do the opposite. So this is multiplication. So you do the opposite of that, which is division. Right? So I'll show it over here. M1 V1 equals M2 V2. So to get rid of the V1, we have to divide it by V1, right? And then you can use this relationship here. A symbol divided by itself is equal to 1. However, the algebraic principle is that anything you do to one side of the equation, you must do to the other side of the equation. Otherwise, you disrupt the equation and it's no longer the same equation, right? So if I divide the left side by V1, I have to divide the right side by V1, okay? So now M1 times V1 over V1 is just M1. And that's going to be equal to M2 V2 over V1. And that should work for any permutation of this equation, right? Any of those that you want to find you can use that approach. Just divide by the one that it's next to, and that will eliminate it from that side and put it over to the other side, right? So often we use very loose language, which is mathematically incorrect. So you might say, oh, move it to the other side. Well, what does that mean to move it to the other side? It means specifically that you do the opposite of the way it's set up. So let's say we want to find V2. Well, that means we want to isolate V2. We want to have V2 equals something, but not V2 times something equals something, all by itself. So if you take a look at it, V2 is right here. It's multiplied by M2. So use this idea here. If I divide this side by M2, that gives me 1. But it's an algebraic equation, so we have to do the same thing to the other side in order to maintain the equation. So if we do that, we now have M1 V1 over M2 is equal to V2. And there you go. Okay. So
Thank you so much.
Yeah, absolutely. Yeah, you'll do that a lot in the next chapter and then in the next chapter after that.
Some of my algebra is rusty.
Yeah, absolutely. But once you get it down, it's fun.
Yeah.
Algebra is actually very fun once you know how to do it. So have a great day, everybody. So I'm going to try to keep doing Thursdays as well, just so we can kind of keep up with the material. Good luck, and let me know if you have any questions. Just go ahead and text me if you need some help sometime this week, okay?
Thank you, Professor.
Very
Thank
good.
you.
You're doing your best.
Thank you. Bye-bye.
Thank you so much for adding
Bye.
Thursday.
Absolutely. My pleasure. My pleasure. Bye-bye, everybody.
Have a nice day.
Bye.